Hi, and welcome to Codex. Today we are welcoming Joshua Grochow, who is at the University of Colorado Boulder. He earned his PhD at the University of Chicago and then was a postdoc at the University of Toronto's CS Theory Group. And after that was an Omidyar Fellow at the Santa Fe Institute. Since then, he has been a professor at the University of Colorado Boulder, where he is in both departments, computer science and mathematics. His research focuses on the interaction between theoretical computer science and mathematics, including a lot of algebraic and geometric questions, and also deciphering the theory of complex systems and networks. So we are very excited to have him here speaking on codes and expansions and algorithms for matrix multiplication. It's always great when the speaker panders to the, the organizers and the name of the seminar. Really looking forward to this. Take it away.
Thanks, Emily. Thanks so much for that very nice introduction, and thanks to you all for having me here. Yeah, what I want to tell you about today, I mean, of course, I want to tell you about some of my work that I'm excited about, but the main message that I really want to give, especially for this audience, is that algorithms for matrix multiplication are really code-like objects, and it's useful and interesting to think about them that way. So I hope to sort of, particularly for this audience, I hope to sort of pique your interest in these kinds of things. And when we say that, okay, normally you think of an algorithm, you think of like computer code, and that doesn't look very much like a code in the coding theory sense. So what do we mean when we say an algorithm for multiplying matrices? Well, I'll start by example, and then we'll get more formal as things go on. Okay, we all know how to multiply matrices, right? You multiply a row by a column. And the measure that we're going to focus on here is how many arithmetic operations you use, so multiplications and additions. So the standard algorithm, right, for each dot product here, there's n multiplications and n minus 1 additions, and you have to do n squared of these, so the whole thing is n cubed steps. And this is an example of an algorithm. And we're going to think of these algorithms very algebraically. So the first thing was in the 60s, it was shown that actually this was optimal if you only work on rows and columns as a whole. So making that precise is a little bit tricky, and I don't want to get into it, but sort of there was this feeling that you really couldn't do better than this. And then in 1969, Strassen showed that actually you could do significantly better than this, getting an algorithm that was n to the log base 2 of 7, which is about 2.81. Okay. And how does this algorithm work? Okay, I don't expect you to follow all of this, but the main thing is, okay, we're multiplying two matrices A and B to get a matrix C, and we're going to start with 2 by 2 matrices. This was somehow the key insight of Strassen's algorithm. And the idea is, okay, you have matrices A and B. We're going to compute these 7 products of linear combinations of the entries of A and B. You don't really have to pay attention to what they are. And then our output matrix, the 4 entries of our output matrix, will be certain linear combinations of these 7 products. Okay, now if you count everything here, the ordinary 2 by 2 product has 8 products and 4 sums. Strassen's has 7 products, but 18 sums. So like, is that really better? And the second insight of Strassen was that this algorithm works even if the entries of your matrix are from a non-commutative ring. So notice here in all of these products, right, the A's always come first and the B's always come second. So now if you're working non-commutatively, that matters. And in particular, for 2 by 2 matrices, you could imagine that their entries are themselves n by n matrices, right? And the beautiful thing about matrices is that 2 by 2 matrices whose entries are n by n matrices, the ring of such things, is isomorphic to the ring of 2n by 2n matrices. So this means that we can do a sort of recursive scheme here where from this little magical thing about 2 by 2 matrices, we can now multiply 2n by 2n matrices using 7 n by n products and 18 n by n additions. So if Rn is the number of products that you need to multiply n by n matrices and an is the number of additions, you get these recursions, right? R2n is at most 7 R of n. So that very quickly gives you n to the log base 2 of 7. And the key thing to notice here is for the additions, you pick up this 18n squared, because adding two n by n matrices takes n squared operations. But then the recursion, you're doing 7 recursive calls. And so you have 7 recursive calls to additions of smaller matrices. Right? And so it's still this 7 that governs the recursion. And so the asymptotic number of operations here is still n to the log base 2 of 7. And this is why you typically in this area, we focus on number of multiplications, that somehow governs the asymptotics when you do this kind of recursive trick. Oh, and I should echo what Emily said. As long as you're not afraid of being recorded, please do stop me with questions. All right, so Strassen said you could do better. And then of course, there's a question, can you do even better? So we defined the exponent of matrix multiplication to be omega, which is the smallest exponent such that you can multiply n by n matrices in n to the e time or n to the omega time. And omega really is standard. If you walk up to a theoretical computer scientist and you say, what's your conjecture for the value of omega, they will all know what you're talking about. The conjectured value, I should say, is 2, meaning that you can multiply matrices asymptotically, essentially as quickly as you can add them. And on its surface, that sounds like a pretty amazing statement, right? It seems like multiplying should really be much harder than adding. And yet we don't have any evidence to refute this, and sort of all of the evidence we have, weak as it is that like, yeah, you can sort of keep getting better and better things. One thing I will mention, which will be relevant if you think about these things in terms of codes as we go on, in principle, this value depends on the characteristic of the matrices you're talking about. We know it doesn't depend on more than that. So it doesn't depend on if you're over F2 or F4, but it could be different if you're over F2 or F3. And for most of this talk, I'm going to talk about the complex numbers. There's actually, even though in principle it depends on the characteristic, there's actually very little we know. Like, I'm not even sure I know one example of something about matrix multiplication where we know something different in some characteristic that's different than what we know in characteristic 0. But in principle, it could happen. Right, okay, so where are we today? So originally back in 1968, the exponent was 3. This 2.81, this was Strassen here. Then there was a long series of improvements in the 80s that sort of culminated with some work of Coppersmith and Winograd in the 90s, in the early 90s. There was no progress for a long time. And then in the last, I guess it's now 9 years, there were a series of results that built on Coppersmith and Winograd that got very minor improvements. So this line looks flat, but it's not. And the current world record is held by Josh Allman and Virginia Vasilevska-Williams from last year. And the reason that I have to write out this many digits is that their improvement over the previous bound was really out here in these last couple of digits. Okay. All right, so this is sort of where things stand. And now I want to get to a little more of back to this question of what do we mean by an algorithm for matrix multiplication? What is the object we're talking about that I want to claim is sort of like a code? And to get to that, I want to really rephrase matrix multiplication a bit more symmetrically. So it's a bilinear map from n by n matrices, pairs of n by n matrices to n by n matrices. And so we can treat it like this, which is to say, this is a 3 tensor, which, okay, I should have really dualized everything. It eats 2 matrices and spits out a 3rd matrix if you dualize everything. And what 3 tensor is it? Well, if Eij is the standard, you have a 1 in the Ij entry and a 0 everywhere else, it's this tensor. Oh, there we go. Right, so if you read this off, this is like saying Eij times Ejk is, well, it should be Eik, right? But actually, because of this dual, we're going to do a transpose in the last coordinate here. And the thing to notice here is if I feed this 3 matrices A, B, and C, and I take the dot product of this tensor with A tensor, B tensor, C, I get the trace of A, B, C, of the product A, B, C. Right, so this here picks out the Ij entry of A, this will pick out the JK entry of B, and this will pick out the KI entry of C. And if what you really want to do is compute the product, right, because this trace thing, it's not exactly matrix multiplication. If what you really want to do is compute the product, well, I can get that by plugging in appropriate matrices for C. I can get any entry of the product AB that I want by plugging in the appropriate matrix for C. Okay, oh, by the way, I think I saw something pop up in the chat, but it disappeared. If it's possible for one of the organizers, if there are questions in the chat, if you could like let me know.
There's a comment that says surely linear from the tensor product.
Yes, yeah. Okay, so this tensor is really what we're going to think about when we think about matrix multiplication. And what is this tensor? Well, I claim that actually this tensor is in some ways quite simple, right? Even though, you know, okay, the complexity of matrix multiplication is this big open question. So think of n by n matrices as I have two n-dimensional vector spaces, and I want to think of the space of n by n matrices as U tensor V. So this is like the row space and the column space. Okay. Then this product, right, the space of bilinear maps from pairs of matrices to matrices, I can write like this, right? So this is my first n by n matrices, my second n by n matrices, and my output. And notice here that because I've done this transpose here, the rows of the first matrix correspond to the columns of the output. The columns and rows, the columns of the first matrix and the rows of the second matrix should match up, and the columns of the second matrix correspond to the rows of the output, again, because of that transpose. Okay, but now if I view it in this space, which is a six-fold tensor product instead of a three-fold tensor product, and I just re-parenthesize, what is this map? It's really a tensor product of three identity maps, right? I'm identifying the columns of the first matrix with the rows of the second matrix. That's this coordinate J here, the fact that these J's are the same, and that's this identity on V, right? Similarly, this U and U star, that's the I and I here, the fact that they match, that's the identity matrix there. And the W and W star, that's the fact that these two indices here match. So in some sense, the matrix multiplication tensor is just a tensor product of three identity tensors. So like, why is there a question? Well, it's three identity tensors, but shifted when you view it as the six-fold tensor product. And when you go back to view it in this three-fold tensor product, it looks like this, and it's more complicated than three identity tensors. Okay, but as a tensor, sort of abstractly, this is what it is. Okay, and now I want to talk about tensor rank, because this will really be our measure of our mathematical measure of the complexity of an algorithm here. So a rank one tensor is anything of the form a tensor product of three things, or a Kronecker product, if you like. So each term in this sum here is a rank one tensor. And we say a tensor has rank at most R if it can be written as a sum of at most R rank one tensors. So if instead of three tensors, I had two tensors, those would be matrices. A rank one tensor, if you only have two factors, is a rank one matrix, right? It's the outer product of two vectors. And this notion of rank is the same as the notion of matrix rank that you're used to, again, if you only had two factors here instead of three. Okay. And why is this a good measure of sort of algorithmic complexity? Well, remember before I said we're going to focus on the number of multiplications that you need, because that somehow governs the asymptotics for matrix multiplication. And there's a theorem, which is now classical, that says that the number of multiplications you need is within a factor of 2 of the tensor rank of the matrix multiplication tensor. Or in fact, for any bilinear map, for any tensor, this is true. Right. So again, if what you care about is asymptotics, this factor of 2 is hidden in the big O notation. So you might as well focus on tensor rank, right? Which is now this beautiful algebraic and geometric thing. Okay, so what do we mean when we say an algorithm for computing matrix multiplication? What I really mean is a rank decomposition of the matrix multiplication tensor. So the set of, by an algorithm for matrix multiplication, I mean a set of rank one tensors whose sum is the matrix multiplication tensor. And these are the objects, these sets of rank one tensors that sum up to the matrix multiplication tensor. These are the objects that I want to sort of hopefully convince you are somehow like codes in some sense. Okay, So just to rephrase what we saw before, Strassen's algorithm says that the rank of the 2x2 matrix multiplication tensor is at most 7. Right? So okay. All right. So before we get to the real part of our story, the meat of like how are these things like codes, I want to pause for a second and say, why are we looking at this thing in the first place, aside from just, okay, it's interesting and beautiful. Arguably, matrix multiplication has tons of applications. It's used in scientific computing, graphics, GPUs, combinatorial algorithms, other algebraic algorithms, and often it can even be the bottleneck in those algorithms. In practice, this is a little bit of a lie in the sense of like, you often in practice have sparse or structured matrices for which much better algorithms are available. And even with dense unstructured matrices, memory and communication issues are more frequently the issue rather than the number of algebraic operations. But Strassen's algorithm, this little trick with the 2x2 thing, that's actually used in practice where you do this recursion down to some level. And then below some level, because of the memory and communication issues, you revert to more standard algorithms. All those other algorithms I showed you on that plot of the best bounds on omega, those are not used in practice today because they have huge hidden constants and memory and communication are an issue. But in principle, there's no reason that there can't be better tensor rank decompositions that actually do yield algorithms like Strassen's that can be used in practice.
Sorry, Josh, real fast. There's been a question about non-square matrices.
Oh, yeah. So you can also talk about non-square matrices, like if you want to multiply an n by m by an m by p matrix. And there are interesting results for some very skew-shaped matrices, like if you have a matrix which is size n by n to the alpha, where alpha is strictly less than 1, so it's sort of very tall and skinny, you can actually get slightly better results. But for sort of general rectangular matrices, there's a trick where you can convert any algorithm for those into an algorithm for square matrices, and so it's still sort of governed to a large extent by omega, by this bound for multiplying n by n matrices. It's not entirely true, again, because this thing of n by, if you multiply a matrix which is n by alpha by another matrix which is n to the alpha by n, again, there are better results. But as sort of a first thing to study, square matrices are pretty good, and they sort of almost capture the general case. Yeah. That's a good question, but I'm not going to focus on that just because I only have so much time. And although I should say many of the things that I say here will apply directly to that case. You can rephrase the rectangular case as a tensor. The tensor rank is still closely related to the number of operations you need, and so on. Oh, right. Yeah, Dustin points out in the other direction, if you have rectangular things, you could pad with zeros to get squares. That's not always the best way, but yeah. Okay, but for us, the more important thing is that this, studying the number of arithmetic operations you need here gives us insight into the nature of computing and complexity and sort of algebraic computation. Okay, so now I want to bring us back to our story. How did Strassen come up with this, right? I just sort of threw up these 7 equations and said, this works. It turns out that actually he was trying to prove that it couldn't be done by hand, by what we can only assume was very clever brute force. And he was trying mod 2, because mod 2, you can really brute force things. And then he found a solution, mod 2, that used only 7 multiplications. And then he figured out the right signs to get it to work over the integers. And once you have it working over the integers, it works over every ring. Okay. But ideally, we would like a bit more of a conceptual explanation for this. And this is where we're going to start to get into some of the connections with codes. All right. So, but maybe before I get to this, are there any other questions about sort of the basic setup, the tensor rank, and so on? Okay. So the first sort of hint of this came in Clausen's thesis in 1988. And to show you what Clausen did, I want to start with sort of a trivial observation, which is take a basis for 2x2 matrices, say the standard basis, EIJ, you know, the 1 in the IJ position and 0 everywhere else, and just write down the multiplication table, right? So it looks like this: E11 times E11 is E11, E11 times E21 is 0, and so on. And from this table, you get a decomposition of the tensor, namely, you know, from this entry, I get this rank 1 tensor, which says E11 times E11 is E11. Okay, and you know, from this entry, I get this this rank 1 tensor, which says E21, that's this E21, times E11, that's this E11, is E21, and that's this one, and so on. Okay. And if you look here, okay, there are 8 non-zero entries here, so I get 8, and that's the usual standard, you know, 8 multiplications algorithm for multiplying 2x2 matrices. What Clausen did was he came up with, in some sense, better bases for 2x2 matrices that let you do better. And I'm not going to say yet where this comes from, because Clausen didn't either. As far as I know, this was just kind of an observation that this worked. So, okay, consider the action of the symmetric group on 3 letters, permutations of 3 things, on a 2-dimensional vector space where the transposition 1, 2 swaps x and y, and the cycle 1, 2, 3 is this matrix, which you can think about. There's sort of this triangle, right? This is the standard vector E1. This is really the standard vector E2. This is like the x-axis, and the third vector is the negative of their difference, and this permutes these 3 vectors, right? So it sends E1, that's the first column, goes to E2. E2 is the second column, goes to this, and if you work it out, this vector goes to E1. Okay, and now to construct our bases, so in both of our bases, we're going to say x0 and y0 are the 2x2 identity matrix. Our next basis matrix is going to be E11, so we'll call that x1. But now, to get the rest of this basis, we're going to look at the orbit of x1 under conjugation by the cyclic subgroup generated by this guy. Okay, and then my y's, yi, will be, I'll take the x's and I'll conjugate them by this transposition 1, 2. Okay, and my claim that I'm not going to prove to you is that these 4 x's, so the identity matrix, E11, and the orbit of E11 under this cyclic group of order 3 by conjugation, that's a basis of 2x2 matrices. And since the y's are gotten from the x's just by conjugation, these are also a basis. So we take our x basis, we take our y basis, and now we write down the multiplication table. Okay, and I claim to you that this is what it is, right? I have no idea how Clausen figured this out. And now, just like we did before, we're going to use this multiplication table to get a tensor rank decomposition. And the key thing here is that, unlike before, where we had 8 non-zero entries in our table and we ended up with 8 terms, now some of the terms combine. So our first term looks very similar, right? We have x0 times y0 is y0, fine. But this, I can actually get these 2 entries of the table in a single tensor because it's x1 times 2 of these things yields the same output. So this x1 is this x1. This x1 is the fact that these are both x1. And I get to combine the y0 plus y3. Okay, and similarly for the x3 here, right, I have the same output in these 2 columns, so I can combine these 2 entries into a single rank 1 tensor here. And if you work it out, what you get is that actually there are only 7 terms here. And the reason is that, okay, you get this one with the y0, that one's special, but then I only have 6 other things appearing here: x1, x2, x3, y1, y2, y3. And how do they appear? Well, y1 appears in a single column, so I can combine those 2. y2 appears in a single column, so I can combine those 2. y3 appears in a single column, so I can combine those 2. x1 appears in a single row, so I can combine those 2. That was this term. x2 in a single row, and x3 in a single row, so I can combine those 2. So the fact that you only see 7 distinct non-zero entries here and that they're in this particular pattern lets you get this decomposition with only 7 terms. Okay. And okay, so this is very beautiful. It's still a little mysterious, but this is actually our first connection with codes. And if you read my abstract, you may recall I said sometimes you have to squint. This may be one of those times. So this is a little bit reminiscent of at least one construction of the Golay code. Okay. So this is similar, as I said, if you squint, and here you really have to squint, to this construction of the Golay code. This is from Thompson's very nice book referenced here. And the thing I just want to highlight, I don't expect you to read this whole page, but is that, okay, he's picking some rows, and then he picks the 11 things that differ from this by an even interchange of elements. Okay. And that's very reminiscent to what we just did, where we took the orbit under the cyclic group, and then we took its coset. There are other things about this construction that are similar to the construction, to Clausen's construction for matrix multiplication, but I don't want to sort of belabor the point here, because even if you go through all the details, there's still a lot of squinting you have to do. Okay, but it's at least suggestive. All right, the second connection with codes goes back to Lempel and Winograd in 76, and this one is not squinty. There's an actual theorem here. So remember when I wrote down Strassen's algorithm, you take these 7 products and then you take some linear combinations of them to get your output matrix. I wrote it this way on purpose. This should remind you of a generator matrix of a code. And indeed, it is. So what Lempel and Winograd proved is not just for matrix multiplication, but in fact for any tensor. If you have a rank n decomposition, so you have n of those rank 1 terms, or you have n products here of a tensor with k outputs, so in this case k is 4, such decompositions correspond in both directions to certain nkd codes where d is lower bounded by something having to do with the tensor. Okay, and for n by n matrix multiplication, that something is n. And so if you have, say, a decomposition with rank n to the omega, which is sort of the optimal by definition of omega, these are n to the omega n squared n codes. And remember, the conjecture is that omega is 2. We know that actually omega, if it is 2, it has to be an infimum, so you can't get 2 exactly, but you can get 2 plus epsilon for any epsilon you want. Okay, now, in terms of like how good codes are, I understand like these are not very good codes, but the point is they're codes. And so you could imagine that there are like things you could do from coding theory, tools you could use to try and study matrix multiplication. Yeah.
Is this characteristic dependent, or can you take codes over some fields that might not be codes in another sense, like the rates contained or something?
Right. No, so this works in any characteristic as long as sort of everything that I've written on this slide, you take in the same characteristic. So you could do it all in characteristic 0, you could do it all in characteristic 2 if you want, and then this omega here should be the omega for characteristic 2, and so on.
Okay, thank you.
Yeah, but their proof, it's just linear algebra. Like they don't need complex numbers or anything, so it works over arbitrary fields. Yeah. Okay. And there hasn't been a ton of follow-up work on this. Like, I think this is a really interesting connection. There ought to be things we can do with this. Yeah, okay, but that's why this is an aside. So that's the end of the aside. All right, so now I want to get back to the story and some of our other, or the main thread of the story. So we've now seen two connections to codes. One was the squinty connection with Golay codes. The other was the theorem of Lempel and Winograd that relates tensor rank decompositions to actual literal codes. Okay, now Clausen's construction was still pretty magic, right? And it starts to feel more codey. There's some special thing happening with incidence something, right? But a few years ago, Chris Moore and I were trying to figure out what we felt was a more satisfying explanation. Like, where does this come from? Why is the rank of 2 by 2 matrix multiplication 7? And what we came across was a unitary 2 design. And I think in the literature, unitary 2 design means many different things. So if I'm using it wrong, you could let me know maybe afterwards, but I'll define everything carefully. So it'll be clear what things are. So, okay, how did we come to this? Well, we started with noticing that matrix multiplication is characterized by its symmetries. And this is an important feature that shows up in geometric complexity theory, which is an approach to P versus NP using representation theory and algebraic geometry. And what does this mean in the context of matrix multiplication? Well, consider let mu be the matrix multiplication map. Okay, what are the symmetries of this map? Well, if I multiply two matrices and I want to know what their product is, I'm multiplying A and B, I could always insert a Y and a Y inverse in between them, and that doesn't change their product. I can always left multiply A by X as long as I also left multiply the output by X, right? If I pulled this X inverse over here, right? And similarly, I could right multiply B by Z inverse as long as I right multiply, again, the output by Z inverse. So these are what I would call the symmetries of the matrix multiplication tensor. These are not all of them. There's some finite group sitting on top of this, but this is the majority of them. And when I say it's characterized by its symmetries, what I mean is for any other bilinear map on the same vector spaces that has these symmetries, that map must be a scalar multiple of the matrix multiplication map. And you can't do better than that, because if I just rescale this by some alpha, that alpha commutes with everything. And so you couldn't hope to have uniqueness any stronger than that. So this is what it means to be characterized by its symmetries. And our starting point was that, okay, say you have a finite group G, and V is an irreducible representation, say n-dimensional. So you can think of your n by n matrices as V tensor V dual, which means G is acting on them by conjugation. Because it's an irreducible representation, and we'll come back to this, instead of being invariant under 3 copies of GLN here, it turns out that invariance under 3 copies of this finite group G is enough to characterize the matrix multiplication map in this way. Okay, so this was our starting point for sort of how we came up to this. And now let me tell you the actual construction here. All right, so remember when we did this sort of shifting before, right? You say, I'm going to write my n by n matrices as rows, tensor, columns. I'm going to do that for all 3 factors. I'm going to reparenthesize. Matrix multiplication looks like, in this reparenthesized version, 3 copies of the identity. And this is actually one way you can prove that it's characterized by its symmetries. Okay, so what we would like is vectors where you get, 3 copies of the identity. So if G is a finite group, say acting irreducibly on C to the n, and S is any orbit of G in here, I guess I should say any non-zero orbit, then by Schur's lemma, if I take the outer product of the vectors in this orbit with themselves and I add those all up, I get some scalar multiple of the identity. Okay, and now if I just do 3 independent copies of that, okay, if I do it sort of the natural way, I get identity, tensor, identity, tensor, identity. But we said if I shift those, that's just matrix multiplication. So I take the same sum, but now I've shifted things. So notice in this sum I have U outer U here. In this sum I have U outer V, V outer W, W outer U. And this is now, okay, this VV here, this is my shifted copy of this VV, so that's my identity on V. This WW here, that's my shifted copy of the identity on W. And this UU here, that's my shifted copy of the identity on U, so this is matrix multiplication. All right, so we're going to say, suppose, now throw away the groups for a minute. Just suppose I have any subset of C to the n, which satisfies this. So when I take the outer product of the vectors in there with themselves and I add those up, I get a scalar multiple of the identity. Then I can do this same trick, right? These are exactly the same equations I had before, but now all I've assumed is this, rather than assuming I have an orbit of some G. Now the bad thing here is that the U, V, and W are really independent, and this has S cubed summands. And if these are n by n matrices, you're going to need S to have size at least n, and so this is going to be at least n cubed. So like this is not going to give us a low rank decomposition of matrix multiplication. So the question is then, what can we do? And we're going to consider this thing instead. So I'm summing, I have the same set S, I have the same assumption on my set S that the sum of the outer products adds up to the identity. And I'm going to consider this sum. So you'll notice here, I still have the VV here, I still have the WW here, I still have the UU here. But now I also have these differences. Now, why would we do this? Well, it kind of looks like matrix multiplication, right? Because if I didn't have these subtraction things here, it would be matrix multiplication. It's, if S is a G orbit, this is almost invariant under G cubed. So that's like almost a proof that this is almost matrix multiplication. But now, because of these differences, the nice thing is I'm really only summing over distinct triples u, v, and w, because if any two of them are equal, then one of these three things is 0, and that term goes away. So I have fewer summands, which gives me some hope of beating n cubed. Okay. And it turns out that this will work. Okay. And not only will this work, but the proof is so simple that I can give you the whole proof here. This is one of the other things that we like about our proof is like you can kind of rederive it and just do the whole thing very quickly. Okay. So if you expand out these things, there are four kinds of terms. There's a totally matched term, right, which comes from if I pick the u and the u here, the v and the v here, the w and the w here, and I pick up a sign. Okay. There's where I have one mismatch. So I still have v matched with v, w matched with w, but over here, I pick the mismatch. So that's the uv. And you could do that in any one of the three places. You could do two mismatches. So here I have a mismatch, here I have the mismatch, here I still have ww. Or you could have all three mismatched. Okay, and what does this give us? Well, the matched ones, this is now the identity tensor cube unshifted, right? This is u outer u. And so I'm summing over all those. That's a copy of the identity. This will give me another copy of the identity and so on. Okay. This one, this is the shifted one. This gives me matrix multiplication. That's exactly the thing I want. And so you might hope that these other terms, when you sum them up, they sum to 0. Okay. And the thing to notice is that in both of these, in the one mismatch case, u only appears once here. And similarly, with two mismatches, there's one vector that only appears once. So one way to get these things to be 0 is if the sum of all my vectors in S is 0, right? If that's true, so this is now an additional assumption on S, then these two terms would be 0, and I wouldn't quite have the identity matrix multiplication, but I'd only be off by a rank 1 tensor, right? I could just add this as another term to my decomposition, and then I get what I want. Now, the nice thing is in the group case, we actually have this, right? Because given a vector in C to the n, this sum, if S is the G orbit of that vector, is precisely the projection of that vector onto the trivial rep. So if this is a non-trivial irreducible representation of my group G, this sum has to be 0 because there's no trivial rep for it to project onto. Okay, so what we get is if S is a G orbit in a non-trivial irreducible representation of G, then I get this decomposition of matrix multiplication. I had to add in this identity tensor cube, but that's a rank 1 tensor, right, to cancel off that first term. And then I have this sum that I walked you through what the four terms were. Okay. And what are these two conditions that we used? Well, these are, let me say, some definition of a unitary 2 design. So in the end, what we get is for any unitary 2 design of size little s in C to the n, you can multiply n by n matrices using s times s minus 1 times s minus 2 plus 1 multiplications. Okay, this plus 1 is for the identity tensor cubed, and this was because we're summing over triples of distinct vectors in S. And again, to James's earlier question, this at the moment, you know, I say unitary 2 design, if I replaced everything with a field F, everything that I just wrote would still work, right? Except the representation theory part. That part gets trickier, right? But in terms of writing down the decomposition and the formula and the number of terms you get, and is it actually matrix multiplication, all of that stuff still works, assuming you have these two conditions over whatever field you want to work over.
But aren't the characters still complex characters, even if you had a different field?
Yeah, okay. Let me just say, ignore the groups for a minute, because I haven't thought about what happens with the groups over other fields. Just if you have a set of vectors over F to the n that satisfies these two conditions, then this is a decomposition of matrix multiplication over that field. Let me say that. I feel confident saying that. I feel less confident if we start talking.
I don't mind a result over C anyway. It's good enough.
Yeah, no, me too. But we'll come back to that. Okay. And
John,
then,
I have a quick question for you. Sorry.
Oh yeah, please.
So it seems like the smallest S could possibly be is n plus 1.
Yep, we're getting there.
Cool. Thank you.
Okay, so the observation, which maybe is very familiar to this crowd, is if G is a finite group and V is a non-trivially reducible representation, and V is a unit vector, then the orbit of V is a unitary two design. Okay. If you think of sort of the natural action of S3 by rotations on C squared, this has an orbit of size 3, which is an equilateral triangle, which should remind you a little bit of the picture that I showed you in Clausen's construction. Okay, and if you plug in 3 here, you get 3 times 3 minus 1 times 3 minus 2 plus 1 is 7. Right. So yes, 3 here getting to Dustin's point is n plus 1. In fact, you have such orbits, right? If you look at the action of Sn plus 1 on Cn, there's always an orbit of this size. This is the smallest possible, which I think is what Dustin was getting at, because the sum has to be 0, so they have to be linearly dependent. Even in that case, you still get something slightly better than n cubed, right? Now, okay, as n goes to infinity, this is not asymptotically better than n cubed, but it's not totally trivial, right? And when n is 2, this is really 7. This is like the right answer. Okay, so now you can ask, okay, that to me at least was a very nice derivation of 7, right? You use this unitary 2 design and you have this sort of very straightforward sum. And it's much nicer than like you write down Strassen 7 equations and just say calculate and see that it works. But you could ask, is this actually Strassen's algorithm, or is this like another algorithm of rank 7? Turns out that the answer is yes. There's a theorem of de Groot from 78 that says that this has to be the case, and I'll say what that is in just a second. But the other thing I want to point out is, in some sense, we don't care, right? What we really wanted was a conceptual explanation of like, where did 7 come from? Okay, now this theorem of de Groot, this is actually our third connection to codes, because this is a uniqueness theorem. This says any rank 7 decomposition of the 2x2 matrix multiplication tensor, they are all equivalent under the action of the symmetry group of matrix multiplication. Right, so I can take those 7 terms, I can put a y inverse in the middle, I can put an x inverse in the middle, I can put a z inverse in between 2 of them. I get another rank 7 decomposition, and because that was a symmetry of matrix multiplication, it's still a decomposition of matrix multiplication. And de Groot's theorem says that in the case of rank 7 decompositions of 2x2 matrices, there's only one orbit of such algorithms. And so this is our third squinty connection. I mean, there's a real theorem here of de Groot, but the connection is squinty, that you have this uniqueness. And this is a little bit similar to sort of the uniqueness of something like the Golay code or other codes. Okay, so what did we do here? We gave a fairly conceptual explanation of where the 7 came from, right? It came from a unitary 2 design, and as Dustin pointed out, the smallest you could possibly hope for in a 2-dimensional vector space is 3, and that 3 gives you the 7. An interesting question here, is to find a similar explanation that works over arbitrary rings. So Strassen's works over arbitrary rings. It only uses 0, plus, minus 1. Ours, we did need some coefficients, right? Because there were scalars on things floating around. And it turns out that you can get away with things as long as you have a half, a third, and root 3 using our construction. And these things come because it's the corners of an equilateral triangle, right? That's where the root 3 is coming from. So I think there are some very sort of arithmetic geometry interesting arithmetic geometry questions here about, okay, if you look at sort of the variety of algorithms, you can ask, when does it have integer points and things like that. And this gets back also to James's question about the fields, right? So our algorithm works just period to give you 7 over fields of characteristic 0 or greater than 3. Okay, other things you might do, well, could we somehow leverage unitary D designs for D greater than 2? And one thing you might look at here is iterated matrix multiplication. So instead of the product of 2 matrices, which corresponds to a 3 tensor, you could look at the product of 4 matrices, which corresponds to a 5 tensor, right? And is there some way that you have some similar sum with different simple differences of things that cancel that would give you some additional benefit beyond what you get from a unitary 2 design? The other thing is, what about other symmetric algorithms? So as in the case of codes and other things, we're very interested in things with a lot of symmetry. There's been a fair amount of work on this in the last 5 years by various subsets of these authors at this point. And in the slides that I post online, I'll include links to all of these things. Okay, so there, this sort of explanation, we really had a unitary 2 design. It's actually like a real thing. It's not squinty. But I did promise in my abstract that there were more connections with codes and code-like things than I would have time for, and I would have 1 slide on them. So that is the slide I will end on. One of the things that we see in matrix multiplication, some algorithms are highly symmetric, as in the works just referenced. Some are not. Some have sort of a mix of symmetry and weird asymmetric terms. And you look at de Groot's theorem, and okay, all the stuff that we like to think about regarding symmetry and optimality and uniqueness for codes and other things, you can also talk about those things in the context of algorithms for matrix multiplication. Coppersmith and Winograd, their result was actually based on arithmetic progression-free sets. And there's been a line of work that sort of expands that. There's an approach that I am very fond of, but didn't get to talk at all about, the group theoretic approach of Cohen and Youmans. This, by the way, is Henry Cohen, who I'm sure you're all familiar with from sort of the packing world, right? This group theoretic approach really has a packing problem at its core. You can also phrase matrix multiplication as like a continuous, now I'm really working over C or R as a continuous minimization problem. And when you do, if you squint, this minimization problem, it looks a little bit like the continuous minimization problems for spherical codes, or like the Thompson problem or things like that. And so you can start to ask about like the energy landscape and local minima and what properties do local minima have and things like, there are all sorts of interesting things you can ask there that are sort of similar to the kinds of things that people ask for the minimization problem in these other contexts. And the last thing I want to mention is there's also a line of research where you start combining algorithms for small matrix multiplication into algorithms for larger matrix multiplication. So this goes back to Hopcroft and Kerr in '71. They did a thing where they took Strassen's 2x2 thing and they boosted it up to, I think it was 2x3 by 3x2 matrices. And you get some advantage from that. Strassen's laser method is sort of along these lines, and it's similar. And now you really have to squint, but it's similar in some ways to this construction of the Leach lattice, where you constrain the bits of the integer entries based on other constraints, which may be smaller codes and things like that. There are also other connections, but I sort of, I can't put them just as a bullet point. They're sort of more involved. But hopefully at this point, I've convinced you that it's interesting to think about algorithms for matrix multiplication in the same vein as all of these other things, codes and packings and so on. And hopefully I've whetted your appetite for more. So I'm happy to take questions and talk to anyone who's interested. Thanks.
All right, thank you very much. Feel free to clap or hit the clap reaction and stop the recording.